Okay, let's review over free body diagrams real quick, and then let's relate them to velocity time graphs and see what happens. And let's do an example case first. And what I'm going to do is I'm going to drive a car from rest by just stepping on the gas. By stepping on gas for 10 seconds. Then remove foot from gas. Okay, so let's look at that. Now, let's look at, we essentially have two separate cases here. We have the initially, when we're pressing the gas, and then we have the no gas system. And although they're similar, they are not necessarily the same. So let's go ahead and take a look at that. First of all, if I draw my schema for the thing, I have a car. I also have the road. I also have the earth. I also have the gas. And I also have friction. Now, there's two ways to handle frictions with a system schema. You can have them coming from the road if you want, or you can draw them as a separate one. I can, to be honest with you, live with it either way. These are my objects here. The one I'm interested in is this one. So I want to draw arrows. Well, friction, and this is where you got to be a little bit careful. Friction is actually going to tug against the car, so we probably want the arrow going that way because it's working against it. Gas is going to tug the car and go the other way. The road is going to push up on it. And of course the earth is going to pull down on it. So then when I draw my free body diagram, and I'll do it right here, I draw my free body diagram. I have FG going down. That comes from the earth. FN coming up. That comes from the road. Those are the same length. They're always going to be the same length if you're on a flat road. Now, I didn't say anything about it being hilled, so we have to assume it's a flat road. The next thing I have is I have the force of the gas. And that comes from the engine. It's also equally correct to say that's the applied force and coming from the gas, or that's the applied force and coming from the engine. To be honest with you, you can do it either way. Now, here's the key thing. We know that if we step on the gas and we're at rest, we're going to get faster. We're going to speed up. We know also that there's friction acting against me. We have the force of friction, and in this case, it's friction from the road. You can put air friction in there too, and if you want to say the road plus air, either one. But the key thing is that's winning right now. The gas pedal is winning. Now, the next thing I'm going to do is I'm going to take my foot completely off the gas. Now, if I take my foot completely off the gas, what's going to happen is I remove this. So my schema would be the exact same, except I don't have this on it. Everything else is still there. So when I draw a free body diagram, tell you what, let's do that in a different color. So what I'm going to say now is I'm going to remove this. That's the no gas part. When I get to the no gas part, now my free body diagram looks like this. Well, I still have FG, that's not gone. It's still caused by the earth. I still have FN. It's still caused by the road. I still have friction. So therefore I have the force of friction from the road. What's gone is the gasoline force. Is this a constant velocity case? No, you have an unbalanced force right here. Is this a constant velocity case? No, you have an unbalanced force right there. Now, if I was to graph it on a velocity time graph, what I want to do is this. And again, this is a little bit new. You've played with velocity time graphs, but we haven't really related them yet to forces. And the only time I was given was the 10-second interval. Well, I know what's happening during the 10-second intervals. I'm stepping on the gas. So what's going to happen is I'm going to get faster. So this represents the gas part. Then what's going to happen here is now I'm going to let off the gas. This represents the no gas part. And that's basically how we put them together. So let's expand it a little bit more. Let's go example 2. Now what I want to do is I want to sketch a graph where I'm leaving the school. I turned out on 108, I stepped on the gas pedal, I got to downtown Columbus, I drove at a constant speed of 25 miles per hour because they will give you tickets. Then I decided that I was going to turn in to get some gas, so I let my foot off the gas. What would that look like on a velocity time graph? And let's label the parts. So this is velocity, this is time. Now I don't have to put units on this because I don't really know what I'm dealing with here. I haven't talked about, it could be velocity, could be miles per hour, could be kilometers per hour, could be meters per second. I haven't really specified that. So again, I'm going from rest to a constant speed for a while, then I'm stopping. Well, what it's going to look like is this. That's when I'm stepping on the gas and getting faster. My velocity is increasing. This is the avoid tickets part. The avoid tickets part is I'm going to drive at a constant velocity. And then I'm going to turn in to the gas station. So I'd have something like that. Now, how steep these are would depend on how fast you speed up and how much you slow down. But this is the only part that's constant velocity. This is not constant velocity, and this is not constant velocity. Now later on we'll play with numerically and do a lot more stuff with that, but I wanted you to at least be able to understand how they relate together. In other words, what areas show which. I hope this helped clear up anything, and we'll talk more in class.